Hello, in this clip I want to talk about production scheduling and machine scheduling. So let's first talk about production scheduling. So what is production scheduling? Production scheduling is the task when you have a number of jobs in which order to put them on one or more machines. So what do you have? Well, you have a number of jobs, and these jobs are characterized by their release date. You cannot start working on them before their release date. The length of their production times, possibly on different machines. There are precedence relations, so in which order should they go from machine to machine, and their due dates, when should they be ready. So the decision variable in these optimization problems are the start times. And the objective, there can be different objectives, but one objective that we use is the tardiness, and we would like to minimize the total tardiness. And the tardiness is the maximum of the lateness in 0, and lateness is defined as the finish time minus the due date. Yes, or due time, but we're used to finish time and due date are both times, but well, we are used to different names. But lateness can be positive or negative. When you're ready early and before the due date, then you have a negative lateness, but in the tardiness we only take the positive part of that. And we want to, as I said, one possible objective that we'll use is the total tardiness, so we sum all the tardinesses over all jobs. And we start with this very simple version of one machine, so you have a number of jobs, release dates, production times, due dates, and in which order should we put them on the machine. So this is called single machine scheduling, and there's a large part of the literature is devoted to these types of problems. So let's think about which constraints we should have in single machine scheduling. Well, assume that you already know that a certain job I goes before a certain job J. Well, because we cannot execute them at the same time on the machine, they should be non-overlapping. So we get this relation. Here you have the production time, the time they need on the machines. This is the starting time. This is their end time. So this way we avoid, this is the time the job I finishes if it starts at xi. So this here is the make sure that these two jobs are non-overlapping. Yes. However, we do not know up front that I goes before j. So we have to first determine the order and then avoid the overlap. And to do that, we introduce binary variables. Yes, so iyj, and iyj is 1 if I goes before j. Yes, and of course either I goes before j or j goes before I, their sum is 1. And now we have an additional constraint in which you will see the y's occurring, and that's the following constraint. So, and here it's the same constraint as we had before, but you added this term here, and we have it for ij and ji. So we have twice this equation with the second one with I and J interchanged. And what is in here? There is a big M. And in optimization problems, when you model optimization problems, you more often need such a big M. And this big M is really big. For example, bigger than the sum of the release dates and the processing times. Now, if I goes before J, then yji is 0. So then you get exactly this equation. So if y goes before j, and in that case yij is 1, then you get the original constraint. On the other hand, the other constraint, because of this yji being 1, because j does not go before I, so then this number is 1, that this number becomes very big, and then this right hand side becomes very big, and then this constraint is always satisfied. So depending on what later our algorithm chooses to do, either this one or that one, you only get one of the constraints corresponding to one going before the other, and not at the same time the other one going before the first. Yes, so this indeed models the order, the non-overlappingness, and the order at the same time at the price of having all these binary variables for every combination of jobs. Next thing we discuss are the objectives. And one possible objective is the flow time. And the flow time, as you see it here, that's the sum of the finish times of all jobs. So xi plus si is when you finish job I, and this is the sum of their finish times. You don't see the due dates in here, but this is for certain problems the good objective. You can also use the make span, again without the due dates in it, and this says, well, I want to finish minimize the time at which I finish my latest job. So this is the time at which the latest job finishes, and then you want to minimize this make span. The question becomes how to model this. Yes, how to put that and model this in a linear way. Yes, so how to model the minimize the make span. Well, actually, minimizing the make span is equivalent to what you see here. You minimize some additional variable z, subject to the constraint that xi plus st must, for all I, must be smaller than g. Yeah? So z will be as small as possible, but it will always be bigger than this. So this is exactly our objective. So this is a way to model this. Another objective, which we already discussed, with the due date, is the tardiness. Yes, now in the tardiness there's also nonlinearity. So here you see the this is here the lateness, and with the plus added to it, the maximum between 0 and this number, you get the tardiness, and we are interested in the sum of the tardiness, in the total tardiness. So how to model this in a linear way? Well, there's again such a modeling trick, which is as follows. So you take the sum of, again, these additional variables, and you assume that all these additional variables are bigger than the lateness, and they cannot be negative. So then the zi's represent the tardiness, and you want to minimize them, and then they will be as close as possible to these numbers, but they will never be negative. So this, indeed, if you minimize the tardiness, then this is the right way to represent it. Okay, now we can put all these things together and come to the integer linear optimization formulation of the single machine scheduling problem. So we saw how to model the tardiness, and actually we have a weighted tardiness. One job might be more important than the other, so the CIs are costs related. You can say CIs are the costs for being 1 unit late on job I. These are the equation David Justels related to the objective. These are the constraints we saw to avoid overlap. These are the 0-1 constraints for the order. This is to make sure that you can only release job when you can start it after the release date. These are to make sure that the y's are binary, that the z's are positive. So this is the full single machine scheduling problem that you can enter in any tool that allows you to solve integer linear optimization problems. And of course you need a solver that allows for that as well. And as you can see, if you would count, and if n is the number of jobs, then you see that you get a quadratic number of variables and constraints. Yes, but there are efficient solvers for pretty big problems. You can efficiently solve this. Of course, when you move on to a multi-machine case, then it really gets big, and the number of possibilities really explodes. And then this is in practice unsolvable. So what you see is that in practice, people who have to solve this, they start in some way finding a bottleneck machine. For example, the machine where the average time is the highest on, or depending on perhaps other constraints. So they find first the bottleneck, they schedule the bottleneck, and then starting from the schedule on the bottleneck, they schedule the other machines. Of course, you can imagine that that is not optimal. So what they end up doing is then often implementing heuristics that do some interchange mechanism to see if they can still improve on this solution. Okay, thank you very much for listening to this clip. Bye-bye.